Hello guys, how are you today? I hope you're all doing well. I'm so sorry for the late post. I came home late today from school, but without further ado, I'm gonna get started with the first question. I'm gonna do again with the answer key. I prefer not to do this method, but sadly, because the internet is acting up again, or the SDP is just like crashing, it's not letting me do my usual method, which is to do the quiz and then submit answer. But in all scenarios, we'll still be able to solve it. We just have the answers in front of us, so it's faster and quicker. So anyways, without further ado, let's get started. Question number 1. Determine the number of sigma and pi bonds in a molecule. What's the number of sigma and pi bonds in CO2? First of all, to find that out, we need to draw the structure of CO2. So we start. C is the central atom. We have oxygen here and oxygen here. Single bond and single bond. We start by drawing the Lewis structure. Carbon is in group 4 plus oxygen is in group 6. So how many oxygen do we have? 2 times 6. That means how many electrons do we have? 4 plus 2 times 6, which is what? Which is 16. But remember, what did we do? We already used 2 pairs of electrons. So that's going to be 2 times 2 electrons. So in total, we already used what we already used for electrons, right? So it's going to be 16 minus 4, which is what? Which is 12. What does 12 mean? That means you divide it by 2, of course, to get the number of lone pairs, which is what? Which is 6 lone pairs. That means we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6 lone pairs or 12 electrons. You always start with the surrounding atoms. Now, what do we need to see? We need to see if the octet is being filled. Now, in this scenario, oxygen has a complete octet. Carbon is missing 4 electrons, and this oxygen is having a complete octet. So what we're going to need to do in this scenario is we're going to need to take a lone pair from this oxygen, and we're going to need to turn it into a double bond. So now the carbon has 3 bonds. We do the same thing over here. We take the lone pair from the oxygen, and we turn it into the carbon. We turn it into the double bond. So now this is what it looks like. If you check, everything is having the proper, the proper number of octet, okay? So they all fulfill the octet. By the way, I forgot to mention that the only few that don't fulfill the octet are beryllium, boron, and aluminum. Only these 3, they don't fulfill the octet, okay? So now, what are they asking us? They're asking us for the number of sigma and pi bonds. We know if it's a double bond, the bottom one is a sigma bond. The top one is a pi bond. Same here. That means we have what? We have 2 pi and 2 sigma bonds. We move on to question number 2. Hopefully this one loads. So in all scenarios, it's going to take time. It seems like there's no escape from the waiting of the quiz to load. Okay, so question number 2 loaded. What does it say in question number 2? Write the first ionization energy of an element X. What do we mean by first ionization energy? It is the energy required to remove an electron from a gas. So what does this mean in this scenario? If we're removing from element X, we need to remove from X as a gas, right? We'll remove an electron from X as a gas. So that's going to be what? That's going to be, after you remove an electron from X gas, it's going to be X positive gas plus E minus. Now this is the first ionization energy. We move on to the second ionization energy. Where do we remove the second ionization energy? From the X plus gas that we obtained previously. So now, it's X plus gas is going to give us what? Is going to give us, you remove another electron, it's going to give us X2 plus gas plus what? Plus electron, E minus. Perfect. We move on to question number 3. We're going to need to wait a bit as well. Okay, question number 3. Okay, why is it easier to remove an electron from 2p in a O2 minus ion than to remove one from the 2p of an Ne atom? In my opinion, look what we will need to do. We'll first need to state that we're dealing with O2 minus and Ne. We'll write their configuration. Of course, they're going to be the same configuration. So 1s2, 2s2, 2p6, and then 1s2, 2s2, 2p6. Same exact thing. After we do electron configuration, what do we check? We check that they are in the same period. If they're in the same period, that means they have the same energy level N, the same shielding effect, as well as what? As well as just that, okay? So it's the same energy level, the same shielding effect, but the only difference is from the nuclear charge, right? So oxygen has a lower nuclear charge than neon. So what happens in this scenario? In this scenario, because oxygen has a lower nuclear charge than neon, that means, first of all, because neon, let me say it this way, because neon has a greater nuclear charge than oxygen, it will attract the same electrons at the same distance with the same shielding effect, stronger, so its atomic radius decreases, whereas the atomic radius of O2- increases. So now, because of this, what can we state? We can state that it's gonna be easier to remove an electron. Why? Because if the atomic radius is bigger, that means the valence electrons are farther away from the nucleus, so it will require less energy to remove it. But if the atomic radius decreases, that means the valence electron is closer to the nucleus. That means what? That means that it's gonna be harder to remove from the orbital. So we're saying that it has O2- has a lower nuclear charge, and because it has a lower nuclear charge, it's easier to remove. We move on to question number 4. What does it say in question number 4? Okay. Question number 4. Electronegativity increases across a period from group 1 to group 17 and decreases down a group. Why is that? We know that as we go across a period, the atomic radius decreases. Why does the atomic radius decrease? Because the nuclear charge increases while the shielding effect and the energy level are the same. Whereas if we went down a group, atomic radius increases. Why exactly is that? Because although the nuclear charge increases as we go down a group, the shielding effect and the energy level also, both of them increase. So these are why that as we move across a period, electronegativity increases, and down a group it decreases, okay? So across a period, nuclear charge increases. Across a period, atomic radius decreases. Down a group, shielding effect increases, and down a group, atomic radius increases. We move on to question number 5. Cobalt chloride may exist as pink crystals of CoCl2, 6H2O, or blue crystals of CoCl2. Which of the following are anhydrous anhydrated? Very simply, anhydrous means that it does not have water, so water is a big no. Hydrated means that it loves water. It's definitely gonna have water with it. So this does not have any water with it, so that's why we call it anhydrous. And this has water with it, that's why we call it hydrated. Now choose the name of the water molecule that are a part of this structure. So why do we say that it's water of crystallization? Well, very simply, they mentioned that they were crystals, and because they mentioned they are crystals, what did we do? We just added the water to the crystal, and especially for the pink one, it's part of the equation of the crystal, so that we will say that it's the water of crystallization. We move on to question number 6. What does it say in question number 6? The composition by mass of a compound Z of general molecular formula. This is what? 40% carbon, 6.7 hydrogen, and 53.3% oxygen. They want the empirical formula. How do we find the empirical formula? To do that, we'll need to do what? We'll need to do a table. Over here, we'll be dealing with carbon, hydrogen, and oxygen. We first start by writing their percentages. What's their percentage? 40%. 6.7% and 53.3%. Let us assume that we took the mass of the compound to be what? To be 100. If that's the scenario, then what does that mean? That means that the mass of carbon in the compound is 40, right? Because if the total mass of the compound is 100, then now the mass of carbon would be what? Let's say mass of carbon would be 40, mass of hydrogen would be 6.7, and mass of oxygen would be 53.3. Now what do we need to do? We need to find the number of moles. How do we find the number of moles? Very simply, we need to do mass over molar mass. So 40 divided by 12, 6.7 divided by 1, and 53.3 divided by 16. So very simply, 40 divided by 12 is 3.33, so I can substitute this by 3.33. This is gonna be 6.7, and this is gonna be approximately as well 3.33. So now what do we need to find? We need to find the simplest ratio. How do we find the simplest ratio? Very simply, you divide all of them by the smallest number, which is 3.33, and you're supposed to get 1 to 1. So the empirical formula of the compound is C1H2O1. Okay? Now, what did they state? In part B, the relative molecular mass of compound Z is found to be 180. Deduce the molecular formula. So how do you deduce the molecular formula? First of all, we need to find an integer, M. No, actually, let's call it, let's use a nice letter. Let us use the letter K. We have the integer K. How do we find the integer K? Very simply. It's gonna be the mass that they found it to be, which is 180, divided by the empirical mass, which is the mass of the empirical formula. So divided by 12 plus 2 plus 16. So 180 divided by 12 plus 2 plus 16. That's gonna give us an answer of 6. That means what do we need to do here? We'll need to multiply this by 6, and thus we'll get our answer to be C6, H12O6. Okay, perfect. Finished from question number 6, we move on to question number 7. What does it say in question number 7? We need to wait a bit. Question number 7. Ionization energies exhibit trends within the periodic table. Locate the graph that represents the first ionization energy variations from left to right across period 3 in the periodic table. So they're talking about ionization across a period. So what do we know about ionization energy across a period? It increases, but it does not increase steadily. It increases at a point, then it decreases, then it increases again, and it decreases, then it increases again, right? So as long as it's increasing, but remember, it increases, then decreases, then increases, then decreases, then increases again, then we can say that this is the first ionization energy. We move on to part B. What does it say in part B? It says, choose the correct answers to complete the following. In general, what do we know? We know that the ionization energy across a period, what did we say? Across a period, we have that the atomic radius decreases and the nuclear charge increases. So it's harder for us to remove the electron, so the ionization energy is going to increase. Whereas if we go down the group, atomic radius increases and nuclear charge increases as well. So we're going to need less ionization energy the more we go down a group, okay? So in general, ionization energy increases across a period and decreases down a group. We know that we're talking about across a period. Nuclear charge increases across a period, but atomic radius decreases across a period. Whereas down a group, the shielding effect increases. And as well with that, the atomic radius will increase. And thus, this will cause a decrease in the ionization energy. We move on to question number 8. What does it say? Okay, question number 8. Drag and drop the correct item to indicate the formal charge for each atom in the nitrite ion. So what do we need to do? We need to find the formal charge. How do we find the formal charge? You take each one, A, B, and C. And now we start. We start with A. Which group is oxygen in? Oxygen is in group 6. So we'll subtract it by the number of surrounding electrons. That's 1, 2, 3, 4, 5, and 6. You consider these as 1. So 6 minus 6, that's going to be 0. That means A has a formal charge of 0. B, which is N. N is group 5 minus 1, 2, 3, 4, 5. 5 minus 5, that's also 0. So we'll get rid of this. Bye-bye. Now, last but not least, we have what we have C. Oxygen is in group 6, right? Minus, now we'll count how many surrounding electrons there are. 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7, that will give us minus 1. How do we check? We add all of the formal charges. So 0 plus minus 1, this will give us minus 1. And this is supposed to be the total charge of the compound. Perfect. We'll move on to question number 9. What does it say in question number 9? Okay, now question number 9. What does it say in question number 9? Which of the following species exists as a resonating structure where electrons are delocalized between the atoms? So let us start. In this question, I'm not going to waste my time by drawing the Lewis structure of everything. I'm just going to take these two because they're resonating structures. I'll draw them and then I will take one more. I think it changed my bad. What the hell? Why did it change? Okay, it was glitching. So anyways, I'm I'm just gonna be drawing for this, and then maybe I will also draw for SiO2 to show you why it's not a resonating structure. First of all, what do we mean by resonating structure? We mean it's something that can change its structure. So let's draw SO2. If we drew SO2, we would have S as the central atom, O here, single bond, right? Now, S is in which group? S is in group 6, plus oxygen is in group 6 as well, and we have 2 oxygen. So 6 plus 6 times 2, that's gonna be 18. Now, minus how many electrons were already used? 1 lone pair, 1 bonded pair, 2 bonded pair, that's gonna be 4 electrons in total. So 18 minus 4, that's gonna be 14. Now, divided by 2 to get the lone pairs, we will have 7 lone pairs. So that's gonna be 1, 2, 3, 4, 5, 6, and 7. Perfect. Now, what do we need in this scenario? We need SO2 to be able to complete what? To be able to complete the octet. As you can see, how many electrons does S have? It has 1, 2, 3, 4, 5, 6. So it's still missing 2 more electrons. How do we do that? You choose any random oxygen. This oxygen is going to be the sacrifice, okay? We're going to choose it and we're going to take 2 of its electrons and turn it into a double bond. So now this is what it looks like. And the double bond could be either over here, or if you choose the other electron as the sacrifice, it would be what? It would be like this. So because it can change, this is why we say that it is resonating. Now, the next one, which is CO3, 2 minus. We start with carbon as the central atom, and then oxygen here, oxygen here, oxygen here. And then carbon is group 4, plus oxygen is group 6, so 6 times 3, that's gonna be 22. Now subtract by the number of electrons that are bonded, so we have 3 bonds times 2 electrons, that's 6. 22 minus 6, that's gonna be 16, right? 16 divided by 2, what is that? That is 8 lone pairs. That means we're gonna have 1, 2, 3, 4, 5, 6, 7, and 8 lone pairs. Now, we forgot something very important, which is what? Which is that it's to the minus 2, right? So it's CO3 minus 2, 2 minus. What does that mean? That means we're gonna go back to the original number of electrons we had, and we're gonna add 2 electrons. Why? Because when we say minus 2, that means we're adding 2 electrons to the original equation. So plus 2, that's gonna be 18. So that is what? That is 9 lone pairs. That means there will be 1 more pair of electrons over here. Now we need to see carbon. Is it beryllium, boron, aluminum? No. If it's not these, it cannot be electron deficient. So it's not electron deficient. What does that mean? It cannot be electron deficient. That means that carbon should complete the octet. So what do we need to do in this scenario? We will take maybe these 2 electrons and we will make them the sacrifice and we'll put them over here. Now don't forget, the whole structure is to the power of minus 2, or it's like brackets minus 2 to show that it was minus 2. You could either have done it like that, or you could have done it like this, or you could have done it like this. So as you can see, the bond is always changing. If the bond is always changing and moving, that means it's what? It's a resonating structure. We now move on to SiO2, which I said would be the last example I'm gonna do. So SiO, single bond, single bond. Si is in group 4. So 4 plus 6 times 2, that's gonna be 16. Minus the number of electrons bonded, so that's 8. So that's gonna be 8 electrons divided by 2, that is 4 lone pairs. Actually, how did I get 8? My bad, it's 4. 16 minus 4, that is 12. 12 divided by 2, that's going to be 6 lone pairs, right? So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's going to be what? 6 lone pairs. Now we check Si. Si is not completing the octet, and it cannot be electron deficient because it's not beryllium, it's not boron, it's not aluminum. So what do we do in this scenario? We need to take the lone pair from here. Now it's still not completing the octet, so we'll take the lone pair from here, and this is what it will look like. Okay, so very simply, as you can see, it's not resonating because we have a double bond on both sides. So very simply, this is why SiO2 is not resonating. Now, question number 10. Question number 10, what does it say in question number 10? Select the picture that represents the Lewis structure of ClF3. What does CnF3 have to be? Cn and then 3F, right? Now Cl is in group 7 plus, also F is in group 7, so that's 3 times 7 because we have 3 fluorine. So it's gonna be what? It's gonna be 4 times 7 basically, which is what? Which is 28, right? So now 28 minus how many bonded electrons did we use? We used 3 times 2, which is 6, right? So 28 minus 6, that's gonna be 22. Divided by 2, that's 11 lone pairs. So let us see. We always start with the surrounding atoms. So that's 3 lone pairs, 6, 9, and then for the remaining 2, we will put them on chlorine. Now, can chlorine have an expanded valence shell? What does that mean? That means it exceeds the octet. Here it does exceed the octet. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has more than the octet. So how do we check if it can be if it can have an extended valence shell? First of all, we check chlorine. In which period is it? As long as it's after period 2. Anything after period 2 is considered what? Is considered able to be electron, or like able to have more than 8 electrons, or able to have an expanded valence shell. So chlorine is in period 3. So because it's in period 3, we can say that yes, it can have an extended valence shell. So that is why this is the answer. We move on to question number 11. What does it say in question number 11? Question number 11. Okay, select the picture that represents the Lewis structure of HCN. How do we do that? We have C, which is the central atom, and then H and N surrounding it, and each one of them gets a single covalent bond. Now, C is in which group? C is in group 4, plus N is in group 5, and then hydrogen is in group 1. So that's 4 plus 5 plus 1, that's going to be what? That's going to be 10 electrons. Now we subtract 4 from it because we use them in the bonds. So that's going to be 6 electrons left. So 6 divided by 2, that's going to be 3 lone pairs. Remember, very, very important rule. Hydrogen never, ever, ever, ever gets a lone pair. So where do the lone pairs go? They go here. 1, 2, 3 lone pairs. Perfect. Now what do we notice? We notice that hydrogen, it does not complete an octet. Hydrogen completes a duplet. And as we can see, it has 2 electrons, meaning it completes a duplet. Carbon completes the octet, but in the scenario, it does not complete the octet. It has only 4 out of 8 electrons. So what are we going to do? We're going to take the lone pair of nitrogen. We'll put it here. Now, it's still missing 2 more electrons, so we'll take the other lone pair of nitrogen and put it here. So now it's going to be H, single bond C, triple bond N with the electron lone pair. We move on to question number 12. What does it say in question number 12? Now, question number 12. Drag and drop to arrange the ions in correct order of increasing size. Remember, what do we need to know? We need to know that the more electrons we take away from an atom, the smaller it becomes. However, the more electrons we add to an atom, the larger it becomes. So in this scenario, first of all, let's check. Are they all belonging to the same electronic configuration? In fact, yes, they all do belong to the same electronic configuration, which is the electronic configuration of argon. Okay? So since they are all belonging to the same electronic configuration, what can we say? We can say in this scenario that always the more positive is going to be the smallest and the more negative is going to be the biggest. That leaves us for K plus in what? In the middle, right? So Ca2 plus, K plus, and Cl minus. We move on to question number 13. What does it say? Okay, question number 13. Now it regards the naming of compounds. Now, they told us potassium reacts with sulfur. Looking in the periodic table, you will need to know what is the charge of potassium and what's the charge of sulfur. We know that potassium is K plus and sulfur is S2 minus. So we do the crisscross and we will get K2S. Now, calcium and phosphorus. Calcium, we know it's found as Ca2 plus. Phosphorus, we know it's found as P3 minus. So we do the crisscross. It's going to be Ca3P2. Then, after that, we have barium and oxygen. So we know that barium is 2 plus, and we know that oxygen is 2 minus. So we do the crisscross, and we will get BaO. We move on to question number 14. What does it say? It says the successive ionization energy value of element X are given in the table below an arbitrary energy unit. So they want us to find to which group X belongs. Very simply, we need to find the greatest jump. So from 450 to 920, that's jumping almost by 2. 1633 divided by 920, that's approximately jumping by 1.7. Now, 6430 divided by 1633, that's jumping by 4. So as you can see, this is a big jump. That means from here, this is the ionization energy 3. This means that this is the group of the element. That means it belongs to group 3. So it belongs to group 3 since there is a great difference between the ionization energy values corresponding to the valence electrons and those corresponding to the core. We move on to question number 15. What does it say in question number 15? Okay, question number 15. Explain why ionization energy generally increases across a period. In general, going across a period in the periodic table from left to right, the first ionization energy of the elements increases. Specify the correct reason for this trend. So when we go from left to right in the periodic table across a period, what happens? We know that the nuclear charge increases, as well that in general, the energy level and the shielding effect, they are the same. So nuclear charge increases, shielding effect is the same. So what happens to the atomic radius? It decreases. So because the atomic radius decreases, what do we say? We say that the distance between the nucleus and the outermost electrons is similar. Why? Because the energy level and the shielding is the same, and the nuclear charge will increase, so that the atomic radius will decrease due to the attraction between the outermost electrons and the nucleus that is increased. So the attraction between outermost electrons and nucleus will increase, and thus this will cause the atom to become smaller, and it will be harder for us to take it away from the nucleus. We move on to question number 16. What does it say? They want, as we go down a group, the first ionization energy. We are going down a group. As we go down the group, nuclear charge increases, energy level increases, shielding effect increases. So although the nuclear charge increases, we have that energy level and shielding effect increases. So the average distance between the nucleus and the outermost electrons increases, and due to this, right, the shielding effect will lead to weaker attraction between the nucleus and the valence electron. So the nucleus and valence electron are farther apart, so they will have a weaker force. So thus, what happens? It's gonna be easier for us to take it away from the nucleus. So that's why we say that it decreases as we go down the group. We move on to question number 17. What does it say? It says the first ionization energy of an oxygen atom is O16.8, is less than that of a nitrogen atom, N14.7. Which of the following statements explain this observation? Select all that apply. The outermost electrons in a nitrogen atom is subjected to less repulsion than that in an oxygen atom. Now, in order for us to explain it, look what we need to do. First thing we're gonna do is we're gonna state everything about O8 and nitrogen 7. First thing, we'll start with the nuclear charge. Nuclear charge of oxygen is greater than that of nitrogen. So now they are what? Oxygen and nitrogen are in the same period. So the energy level is the same. The shielding effect is also the same. So when they are the same, what do we do in this scenario? We resort to the last thing, which is the box. So let's write the electronic configuration of them. It's going to be 1s2, 2s2, 2p4. And this is 1s2, 2s2, 2p3. Now let's draw the boxes of the last shells, right? So this is gonna be what? This is gonna be 1 up, 1 up, 1 up, 1 down, and then this is gonna be 1 up, 1 up, and 1 up. So in the last orbital, the last p orbital of oxygen and nitrogen, oxygen experiences more electron-to-electron repulsion, which makes it easier for us to take away the electron, whereas nitrogen experiences less electron-to-electron repulsion. So thus, it's gonna be what? It's gonna be harder for us to take away the electron. We move on to question number 18. What does it say in question number 18? Question number 18, what does it say? Question number 18. The first ionization energy of a gallium atom, 7031 gallium, is less than that of calcium. Why is that? First of all, we need to do the configuration of gallium and calcium. Gallium is gonna be argon 4s2, that's 20, 3d10, that's 30, and then 4p1. Now, for calcium, it's also argon, but it's only argon 4s2. So now, what did they say? They said that the reason that the outermost electron in gallium is less penetrating, why? Because the outermost electron is in the 4p orbital, and it's in front of it, it has 3d10, and then 4s2, and then argon, right? So it's less penetrating. It does not go to the nucleus as much as the calcium, because calcium is only, the only barrier it has is argon, right? So, because it's less penetrating towards the nucleus, it's subjected to more shielding by the 4s electron, and less nuclear attraction, because it's very far away from the nucleus, so the nuclear attraction is less. So thus we will say that it's gonna be easier for us to take away the electron from gallium. Okay, so that is it for question number 18. Let's move on to question number 19. What does it say? It says, styrene is a hydrocarbon used in the manufacture of polystyrene plastic. It has the following percentage composition by mass. C is 92.3%, hydrogen is 7.7%. What does this mean? This means we need to draw the table. So we have carbon on top and hydrogen here. So 92.3% and 7.7. Whenever we have percentages, we will always assume that the total mass of whatever we have is 100, right? That means if we were to find the number of moles, it would be mass over molar mass. So 92.3 over 12, how much is that? That's gonna be almost 7.7, and then 7.7 divided by 1, that's 7.7. So now we get that to be the simplest ratio, 1 to 1. So the empirical formula is CH. Now they told us that the relative molecular mass is 104. That means to find the value of K, we're going to do 104 divided by the molecular mass of this, which is 12 plus 1, which is 13. Right? So this will give us an answer of 8, if I'm not mistaken. Yes, so now we need to multiply this by 8 and we will get C8H8. Perfect, we'll move on to question number 20. What does it say in question number 20? Question 20. Which of the following is the correct dot and cross diagram for BAF2? First of all, when we look at BAF2, we will see that it's a metal plus a non-metal. So when we're dealing with this, we will not use the joined atoms that are sharing electrons. No, we will use these representations, because when we have ions, it's an ionic, right? So when we have ions, we will be using these representations. So Ba for sure is Ba2 plus, right? And how many Fs do we have? We have one F, two F, and they are both F minus. So far it's correct. Now, how do we denote F minus? We have to make sure that it has 7 electrons, and the last given electron is from somewhere else. That means it's different, it's not a dot. So this is correct for sure. This is wrong because it's not F2 minus, and we said these two are wrong because they're not sharing electrons. And again, this is wrong because it's not F2 minus, it's F minus. So the correct answer is A. We move on to question number 21. An element Z has the following electronic configuration. So how do you find in which period it is? You look at the number of the very last S, which is 4. That means it's in period 4. And how do you check the group? You add the from the valence shell, which is the 4s4p valence shell, you add the electrons. So 2 plus 5, that's gonna be 7. That means it's gonna be in group 17 or group 7a. Okay? So the answer is D. We move on to question number 22. What's the correct shorthand electronic configuration for element X? It's unreactive, meaning that it's a noble gas and in period 5. So you open your periodic table, you will see where is period 5. Okay, what's the noble gas in period 5? It's xenon. So they want the electron configuration in terms of like this, and you just write whatever. So what's the noble gas previous to xenon? It's krypton, right? So it's gonna be krypton. Krypton 5s2. Why? Because krypton ends at 4D if I'm not mistaken. So it's gonna be what? It's gonna be krypton 5s2. First of all, how many electrons does krypton have? It has 36 electrons. That means xenon has 54. How many do we need to find left? 54 minus 36. We still have to fill in 18. So we just used 5s2. It became 18 minus 2, which is 16. Then 4d10. That's what? That's 16 minus 10, which is what? Which is 6. And then last but not least, it's gonna be what? It's gonna be 5p6. So 6 minus 6 is what? It's 0. So this is the final format, or you can switch it up. So this is also correct. We move on to question number 23. What does it say in question number 23? Hopefully it loads for us to see what it says in question number 23. Question number 23. Which of the following would be the correct electronic configuration? What do we need to do? We need to find out where was the biggest jump. So we start counting all of the jumps. So what do we need to do? You just need to do the current ionization energy divided by the previous one. So 2298 divided by 1251.2, that's gonna be 1.8. Then 3822 divided by 2298, that's gonna be 1.6. Then 5158.6 divided by 3822, that's gonna be 1.3. Then 6542 divided by 5158.6, that's gonna be 1.2. Then 9362 divided by 6542, that's gonna be 1.4. 11018 divided by 9362, that's gonna be 1.17. And then 33604 divided by 11018, that's gonna be 3. So the biggest jump occurs over here. That means it is in group 7A or group 17. That means the valence electrons, it has how many valence electrons? It has 7 valence electrons, right? So what do we need to do in this scenario? We will need to find the one that will end with what? That will end with 7 valence electrons. So what do we need to do in this scenario then? We'll need to look to all of the valence shells. For example, let's take all of the valence shells, this, and this, and we add them. We add the electrons all together to see if they will give us 7. So this is 8, this is 4, this is 5, this is 7, and this is 6. So for sure, this one is gonna be our answer. We move on to question number 24. Which of the following about electrical conductivity is true? Aluminium has the highest electrical conductivity because it has the highest number of delocalized electrons. Whenever they state electrical conductivity, the only thing we should be talking about is delocalized electrons, and that's it. So cationic radius, free-flowing valence electrons, giant molecular, and strong ionic is all wrong because it's about the delocalized electrons only when we're talking about electrical conductivity. 25. Nitrogen and fluorine are both elements in period 2. Yes, that's true. What do they want from us? Nitrogen has a lower effective nuclear charge, so its valence electrons experience a weaker attraction to the nucleus. What did we say from this? Which of the following best explains why the atomic radius is smaller than... okay, so we're talking about atomic radius. Fluorine and nitrogen. Let's do comparison. First, starting with nuclear charge. Fluorine has a greater nuclear charge than nitrogen. However, they are on the same exact same exact period. So their energy level is the same. Their shielding is the exact same. And then last but not least, what do we resort to when it comes to this? When we have shielding the same, energy level the same, and all of this, the last thing we will resort to is what is, of course, if it does not contradict what we say usually. We said that as we go across the period, the atomic radius decreases, right? So it does not contradict what we're saying. We're saying that fluorine is smaller than nitrogen. So if it does not contradict what we're saying, we just say that because nitrogen has a lower effective nuclear charge, its valence electrons experience a weaker force of attraction to the nucleus, so they're farther apart and the atomic radius is bigger. We move on to question number 26. What does it say? Hopefully it will load. Question number 26. Which of the following have a coordinate bond? So I'm just going to take the two that have a coordinate bond. I'm going to draw and I'm going to explain what a coordinate bond is. We first start with NH4+. So N, right? We have hydrogen here, hydrogen here, hydrogen here, right? Originally, what happened? It was NH3, and this is the structure of NH3. I'm gonna leave it for you to get it, right? Then what happened? Then they decided, okay, this is NH3, it's boring, let's take H+. Let's see what happens when we bring H+ close to the NH3. It will become NH4+. But we know that when we form a bond between two nonmetals, it's the sharing of electrons. But in this scenario, hydrogen was positive. It did not have any electrons, and nitrogen had 2 electrons. So what happened? Nitrogen gave these 2 electrons to hydrogen to bond. And because of this, we say that this is a coordinate bond. Perfect. This is the first example, NH4+. The second example, Al2Cl6. We can do that. We can achieve that by drawing 2 structures of AlCl3. So, Al can be electron deficient, right? Cl, on the other hand, cannot. So let's see, Al is in which group? It's in group 3. Plus 7 times 3, so that's gonna be 24. Minus, how many electrons did we use already? We already used 6 electrons because we have 3 bond pairs. 24 minus 6, that's gonna be 18. Divided by 2, that's 9 lone pairs. So that's gonna be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is what a classical AlCl3 looks like. This is not a coordinate bond. However, if you get another AlCl3 and you place it here, like this, right? Look what happens. Very simply, Al is what? Al is electron deficient. Cl has a lone pair. So what does it do? It will give the lone pair and it will make it a bond between Al and Cl. Same exact scenario here. So this Cl will give this lone pair and make it into a bond. And this is why it's a resonating structure, because the 2 electrons came from Cl itself. So that's pretty much it for question number 26. We move on to question number 27. Hopefully it won't take long to load. Question number 27. Which of the following has the largest bond dissociation energy? Very simply, how do we find the largest bond dissociation energy? We very simply need to find out which of the following bonds has the greatest, which of the following has the greatest number of bonds. So I'm gonna draw them all. You guys should know how they are supposed to be drawn. Okay, so this is N2, this is Cl2, this is H2, this is F2, and this is O2. Okay, so which of them has the largest bond dissociation energy? What does it mean? It means the energy required to break the bonds. Definitely, if it's a single bond, it's easier to break than a double and triple bond. And if it's a double bond, it's easier to break than a triple bond. So our winner is N2. Now, which of the following have a bond order of 1, meaning they have only one single bond? Again, let's draw their structures. I have them memorized. You can have them memorized, or you can do them like the loose structure. Of course, it's up to you in the end. So Br is like this. I is like this as well. And then H2 is like this. So which of them has a bond order of 1, meaning it only has one single bond? So Br2, I2, and H2, very simply. We move on to question number 28. What does it say? It says, what's the Lewis structure of PO43 minus? So let us start. PO43 minus P. And it has, how many O's? It has 4 O's. Perfect. Now, we should know that PO43 minus, first of all, is a resonating structure. That means we can directly eliminate this and, we can directly eliminate that and this as well. Now, we start with the Lewis structure. It's gonna be P. P is in which group? P is in group 5. Plus 6 times 4, which is 24. Because oxygen in group 6, 4 oxygens. That's gonna be what? That's gonna be 29. Now, we have minus 3, so we're going to add 3 electrons. That's going to be 32. We will now subtract by the number of electrons used. So that's 4 times 2, which is 8 electrons, based on the bonds, of course. So 32 minus 8, that's going to be what? That's going to be 24. 24 divided by 2, that is 12 lone pairs. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, what do we do in this scenario? we will need to check the formal charges and we will need to change it based on the formal charges. So we know that the total charge should be what? It should be minus 3. So let's say we have let's label A, B, C, D, and E. Let's say we have the formal charges of A. It's gonna be the group number, which is 6, minus the number of electrons, which is how much? Which is 7. So it's minus 1. If that's the scenario, then it's minus 1, minus 1, minus 1 over here. And over here, it's gonna be what? It's gonna be plus 1. So it's gonna be minus 4 plus 1, which is minus 3. But we have an issue over here. We need it to be the most stable. In order for it to be the most stable, we will need our central atom to have a charge of 0. So we need to make it in a way that the central atom has a charge of 0. What could we do possibly? Possibly, we could take the electron from here. We can make it a double bond, right? If we do that as well, look what happens. If we do that, this will become 6 minus 6 electrons, which is 0. So now we have 0 over here and 0 in the center. So as long as our central atom has a charge of 0, then we will be what? We will be just fine. So this is the final structure. Don't forget to put the minus 3. So that means this is our structure over here. We move on to question number 29. Copper disulfate exists as a blue crystal in hydrated form, right? So they want us to find the value of X, okay? They told us that the relative molecular mass of all of this is 249.5. So what do we know? This is the mass of copper sulfate multiplied by the mass of water. So what's the mass of copper sulfate? The molar mass of copper sulfate. It is 63.5. Sorry, it's not divided, it's added. My bad, my mistake. So this is the molar mass of CuSO4 plus the molar mass of H2O added together to give us this. So it's 249.5 minus 63.5 plus 32 plus 16 times 4. So that's gonna be that's gonna be 90. So 90 is now what? It's the mass of what? Of water. So it's gonna be 90 divided by the molar mass of water, which is 18, and this will give us the value of X to be what? To be 5. Very simply. We move on to question number 30. What does it say? Okay, this is easy. If there's only one intersection, like here there's only one intersection, then directly it's sigma bond. Here as well, it's only one intersection. Why did I choose pink? It's not that clear. Here it's what? It's two intersections. Look very, very clearly. One intersection here and one here. So it's gonna be what? It's gonna be a pi bond. And then last but not least, this is only one intersection. That means it's what? It's a sigma bond. We move on to question number 31. What does it say? The combustion by mass of compound Z of general molecular formula CXHYOZ is 54.5% carbon, 9.1% hydrogen, and this much percent oxygen. They want the empirical formula of compound Z. Very simply, what do we need to do in this scenario? We need to do a table, right? So we're going to have what? We're going to have carbon, we're going to have hydrogen, and we're going to have oxygen as well. I think carbon needs also a bigger space, yeah? So let's take the masses. We said that the total is how much? Is 100. That means this is 54.5% or 54.5 grams, 9.1 grams, and 36.4. Now to find the number of moles, you do mass over molar mass. So 54.5 divided by 12, that's gonna be 4.5. 9.1 divided by 1, that's gonna be 9.1. And then 36.4 divided by 16, that's 2.27. Now, we need to find the simplest ratio, so you divide them all by 2.275. So it's going to be 4.5 over 2.275, which is approximately 2. 9.1 divided by 2.275, which is 4. And then 2.75 divided by 2.275, which is 1. So it's C2H4O. Perfect. Now, how do you find the molecular formula if they give you the mass? The mass is 88 divided by the empirical formula mass. So it's going to be 2 times 12 plus 4 plus 16. So that's 44. So the given mass divided by the empirical mass, which is 44, will give you a ratio, which is 2, right? So that means we'll need to multiply all of this by what? By 2. So it will be C4H8O2. Now, last but not least, question number 32. This is the naming. It's easy. So oxygen difluoride, it's definitely oxygen. Fluorine, di means we have 2 fluorines, so OF2. Manganese trichloride, manganese is Mn3. That means it's 3 plus, chloride is Cl minus. You do crisscross, MnCl3. Now calcium hydroxide, what's calcium hydroxide? It's calcium Ca2 plus, hydroxide OH minus, crisscross CaOH2. And then last but not least, lithium hydrogen carbonate. Well, very simply, it's lithium plus, and hydrogen carbonate is HCO3 minus. So you do the crisscross, it will be LiHCO3. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful